But what happens if the number of groups that you are planning to compare is more than 2? Instead of just males and females, for example, you want to compare a group of 5 groups of people who voted for 5 different political parties, and for each group you have, for example, IQ score measurements, and you want to test this hypothesis. Then, in order to compare several groups at once, you need to use another bunch of statistical tests. Tests for comparing several samples. Again, these samples can be independent or dependent. Independent samples are usually individual in the different groups of individuals. People who have a Mercedes, people who have a Porsche, or people who have a Renault car, for example, and so on. Related samples or dependent samples are related groups of observations. For example, scores of the same individuals at 3 different data points in September, October, and November, for example. And how is the hypothesis formulated? The general hypothesis that is tested by all these statistical tests is called also an omnibus test. Omnibus from Latin of all. Basically, it tests the hypothesis whether all of these samples come from the same population, come from one population. If your p-level is not significant, you can assume that there are probably no differences between those groups or between those time points. But if your significance level is good enough, you can conclude in favor of H1 that maybe all of these samples do not come from the same population. But then another question is which of these groups differ from which of these groups? Because you might have a situation when you have 3 groups that are kind of the same, and it's only one group that is different from all the rest significantly. This is why after this omnibus test, in case if it's significant, you also need to conduct additional tests to compare these groups individually to find out which of them is different from which. And here, just like with the t-test, we have several options. The parametric option, which is basically a generalization of student t-test, is called analysis of variance, or just ANOVA, invented by Ronald Fisher. That's why it uses an F statistic named after Fisher. And it exists for independent samples. It's called then one-way ANOVA, or for related samples. Then it's called repeated measures ANOVA, and they both live in SPSS under analyze compare means. However, if you want to use a non-parametric test, you have a Kruskal-Wallis ANOVA kind of, or Friedman's ANOVA kind of, that live under analyzed non-parametrics, K independent or K related samples, respectively. So let's just take a quick look at one-way ANOVA to figure out how we can use it. Because it's basically a generalization of student t-test, it can be applied to the same type of data, and it makes the same assumptions. Basically, if you compare just 2 groups with ANOVA, the result you will get will be exactly equal to student t-test. You will get exactly the same significance level. So when some people say, oh, you have 2 groups, why do you apply ANOVA? Well, because it makes no difference. Of course, student t-test might be simpler, but it makes no difference at all. So ANOVA assumes that your variable which separates those groups is nominal, and the variable on which you are comparing those groups, your target variable, is interval. It is also called dependent variable. And the variable which separates the groups is called factor sometimes. Because in an experiment it used to be a causal independent variable, but of course when we apply ANOVA we don't make any assumptions about causality. However, the assumptions that we make concern normal distribution on the variable which you're comparing in each of the groups that you're comparing. And also homogeneity of variances. Just like with the t-test, your Levene test should not be significant. Or you can use a rule of thumb. The largest standard deviation that you see across your groups and the smallest standard deviation that you see should not be different more than by twice. If you see a larger difference in standard deviations between individual groups that you're comparing, then probably you need to be careful and you need to use a variant of ANOVA which does not assume equal variances. And such an ANOVA also exists, and it is also called Welch's ANOVA. In SPSS there is another version which is called Brown-Forsyth, which is another type of adjustment for unequal variances. However, what is common for both of them? ANOVAs with this adjustment, they are more robust in case if your variances are really unequal. However, when your variances are equal, it is a regular, normal ANOVA, which has more statistical power. That's why with two groups it does not make any difference which one you're using, standard t-test or Welch's adjusted t-test. But for ANOVA, for equal variances, normal ANOVA is more powerful, and for unequal variances, Welch's ANOVA is more powerful. And of course, your distributions must be normal in any case. If your distribution is not normal, you need to use a Kruskal-Wallis test, non-parametric alternative. When we apply ANOVA, there are several types of hypotheses that we can make. The first type of hypothesis is called planned contrast. The standard hypothesis that you are testing in ANOVA just tests whether all these samples come from the same population. So it's a non-specific hypothesis. However, sometimes before actually analyzing your data, you might have a more specific expectation. For example, you're having a control group and you're having two experimental groups with two different interventions. And you might have an expectation that, for example, control group has a lower score and both of your experimental groups should have higher scores and the same. Or you might have another expectation that you have a control group, an experimental group with a weaker intervention where scores should be higher, and another experimental group with a stronger intervention where the scores should be still higher than in the previous group and in the experimental group. So if you have this type of expectation, you might want to test a hypothesis which is called planned contrast or planned comparison. It is only useful in planned experimental studies. And the type of relationship between the scores in those groups can be different. It can be either, for example, linear, or it can be set arbitrary. When you set it arbitrary, you supply to SPSS what is called contrast coefficients. For example, here we are comparing two groups, and we have an expectation that two of these groups should have low scores and equal scores. Another group should have a higher score, and the fourth group should have a still higher scores. So then you basically create these contrast coefficients for those four groups. The only rule is that the mean of these contrast coefficients should be 0. And in Field's book, in case if you want, you can always find a description of how these contrast coefficients are created, or just Google it up. In principle, it's not often that we have these a priori expectations that are so specific. But if you have them, you can test this planned contrast. And then in SPSS, you'll get a separate table, which is called contrasts, where you will have significance for this particular planned contrast. And this significance might be even stronger than for your main omnibus test, because it's a more specific expectation. But if you don't have such a specific expectation, don't test it. Most often, we test another type of hypothesis called post hoc tests. Post hoc means after this. They are also called a posteriori tests. because they are conducted after you actually test your main omnibus hypothesis. So if you have many groups and you see that your omnibus test is significant, your ANOVA produces a significant result telling you that those groups don't come from the same population. You are interested which of these groups are significantly different from which. And of course, you could use a simple student t-test. Just compare each group with each other group and get your results. However, the problem that you have here is that when you have many groups that are being compared, your chances of committing a type 1 error increase. Because if you test your hypothesis at p less than 0.5 level, there is a 1 in 20 chance of observing a significant difference just by chance alone. And because you have so many of those comparisons, of course, if you have just 3 groups, probably it's no big deal. The increase in the probability of a type 1 error is not very large. But if you are comparing 7 groups, for example, then the number of individual comparisons between those groups is 21. And your probability of finding a difference just by chance that you will consider significant if you just use normal t-test is fairly large. That's why it makes sense to use not a simple student t-test, but to use some kind of post hoc test that adjusts for the number of comparisons that you make. And as we discussed, there are different types of adjustments that you can make. That's why in SPSS you choose between different post hoc tests. The easiest one is called Fisher LSD test. LSD does not mean what you are thinking. It means least significant difference. And it's basically a version that offers no protection against multiple comparisons. But it's more likely to be significant. So if your sample is small, you want to have higher power, you can use LSD. Not LSD, but Fisher LSD test. A more common version is called Tukey HSD. HSD is for honestly significant difference. And it makes a moderately conservative balanced adjustment, which is probably the best in most situations. If you want a very conservative adjustment, it's Bonferroni test. However, it's extremely conservative, so you won't see any results by chance, but you will also cut on your statistical power. And in case if some of your groups are control group, in case if you have a control group, you might want to use a Dunnett test, which compares all groups against one of them. Or there are specific versions of these tests for unequal variances. So basically, all of these post hoc tests, they kind of use the same approach. You have, for example, here 3 groups, beginner, intermediate, advanced, and each of these groups is compared to each of the other groups on your dependent variable, and you get a significance, and you get an estimate of difference between the means, and you can calculate Cohen's d if you want. Newer SPSS will probably give it to you automatically if you check the effect sizes box. So you can use this to conclude which of the groups differ, and you can also look at the graph at the plot of means to kind of understand the logic of these results. Another tricky point concerns effect sizes. So the results of your ANOVA test in SPSS normally look like this. It's just a table, and the total variance that you see in your sample on your variable is separated into 2 portions. The variance that is associated with belonging to different groups, it is called between group variance, and the portion of variance that is associated with just individual differences within each group, it is also called within group variance. So for each of these variance estimates, you have a number of degrees of freedom, and as a result, there is an F statistic which is compared against critical values for these particular degrees of freedom, and you get this significance. which basically is an estimate whether this proportion of between group variance is statistically different from 0, which means that your groups come from different populations. If you want to calculate an effect size, if you are using an older version of SPSS, for a one-way ANOVA, calculating an effect size is very straightforward. You just need to divide your between group variance by your total variance. And you get a proportion of variance that is explained by group membership, that is explained by your independent variable. This proportion is called eta squared, and it's very similar to r squared. It is also a proportion of variance. In newer versions of SPSS, you can just check the box effect size and you will get this eta squared and a bunch of other effect sizes that you can interpret as proportion of variance of your dependent variable associated with your independent variable. So for example, proportion of differences in anxiety associated with gender. And this is comparison between males and females. And when you present your results of your ANOVA, you can present it in a table. If you have many variables, then for each variable you give ideally some descriptive statistics for each group, F statistic with significance and degrees of freedom for effect and for error, and effect size, which is normally eta squared. However, if you have a few variables, you can just present your results in the text. For each group, you can give M and SD, mean and standard deviation, at some point. And for each comparison, you can just state your results like this. The effect of treatment on anxiety was significant. For example, if you're comparing a control group and two intervention groups. And here for F statistic, you have 2 degrees of freedom. For effect, which is the number of groups compared -1, and for error, which is the number of individuals minus the number of groups. The value of this F statistic, significance, and eta squared. So this effect explains 3% of variance. It's not very strong, but it's not super weak either. So this is one-way ANOVA for independent samples. And just as another example, this comes from our paper with Anna Malutina and Natalia Koshleva, where we had students who were given a creative task, and we had 2 experimental conditions, high meaning condition and low meaning condition. And for each solution, we had an estimate of how original it is and how realistic it is. And here for ANOVA, we see that the results here are significant, and we can compare the 2 groups using the plot of means. It comes from an older version of SPSS, so this plot is not so nice. It does not have bars for confidence intervals. As a result, it's almost impossible to use this plot because if you want to really illustrate your findings, you need to show confidence intervals for each group, and then just by looking at the plot, it's already possible to tell whether these groups are statistically different from one another. And here, because it was older SPSS, we calculated these effect sizes by hand, and yeah. So how do you deal with violations of your assumptions in ANOVA? If your Levene test is significant, you can simply use a robust ANOVA and not worry about anything else. In SPSS, you have Welch's ANOVA and you have Brown-Forsyth ANOVA. However, if your distribution is not normal, you need either to transform your data. Sometimes you can screen out outliers. Sometimes if you have what is called a heavy tail, a long tail on the higher end, we apply square root and it makes the data more normal. Or you can use Kruskal-Wallis test instead. A version of ANOVA for dependent samples is called repeated measures ANOVA. It's pretty much the same thing as your normal ANOVA. The only difference is that it compares measurements coming from the same group of people or measurements that are related in some other way. So here, as an example, I have scores on 3 quizzes taken by your predecessors last year. And these are scores on a 10-point scale for each student for quiz 1, quiz 2, and quiz 3 in our research methods course. So I was interested whether the mean scores on these 3 quizzes are similar or they are significantly different, and it suggests that probably students either the quizzes are not equally difficult, or maybe the students' level of preparation is not the same. So when I set up repeated measures ANOVA, I have these 3 variables with measurement level set correctly to scale, and I go in SPSS to analyze general linear model repeated measures, and there I need to set up my factor. So I need to tell what is the name of my variable, which determines the differences between these measurements. For example, quiz number or time if it's repeated measures, pre-test, post-test follow-up. And how many measurements do I want to compare? Here I tell SPSS 3, I say add, and I say define. And then for these 3 levels of this independent variable, which is within group variable, I just need to assign measurements. So I simply drag my quiz 1, quiz 2, and quiz 3 to these 3 levels. And as a result, I get pretty much the same findings. I have a plot of means, which I can use to find out that on the 3rd quiz the students were more successful than on the 1st and on the 2nd. And I see that these differences here are strongly statistically significant, and also SPSS provides a measure of effect size which is called partial eta squared. So about 43% of all the differences between individuals are associated with the number of quiz rather than with differences between the students or measurement error. So this was just normal ANOVA. If you want to use its non-parametric alternative, you need to use Kruskal-Wallis ANOVA. It is basically an ANOVA but performed on ranks. So you just like Mann-Whitney test. Basically you take your data, and instead of using the real data values, you just rank your individuals, you give each individual a number in this set, and you work with those numbers. That's why it kind of loses some information in your data. That's why it's less powerful when your distribution is perfectly normal and your scale is interval. However, if your scale is ordinal, or if your distribution is very different from normal distribution, then Kruskal-Wallis ANOVA will be more robust. However, it still has an important assumption. It assumes that your distribution has the same shape in different groups. If this assumption is violated, you can get all kinds of misleading results, false negatives, false positives, etc. So just be careful. Sometimes if your distribution is slightly non-normal, but your variances are very different, it might be Welch's ANOVA that might work better than Kruskal-Wallis. And the results that it gives you here are pretty much the same. You get a chi-square statistic, and you get a significance level, which can tell you whether the ranks in those groups are different, not just by chance alone. And you can calculate an effect size, an eta squared estimate, just by dividing your chi-square by the total number of observations minus 1. Unfortunately, SPSS does not give you any post-hoc tests for Kruskal-Wallis ANOVA, and you need to just perform Mann-Whitney by hand. Or in R, it gives you post-hoc tests that are appropriate. I can't remember about Jamovi. Never tried it in Jamovi. A version of repeated measures ANOVA for non-parametric statistics is called Friedman's ANOVA. It is a very rare situation, actually. I've never used Friedman's ANOVA in my life, because every time I have repeated measures, usually the level of measurement is stronger than ordinal, and the distributions are fairly close to normal. However, if you have stuff like expert ratings on an ordinal scale, for example, you might want to use Friedman's ANOVA to check whether these experts give different ratings or some other type of hypothesis. But usually, if you have expert ratings, you still use other statistics that are more important here, statistics of expert agreement rather than of differences between expert ratings. So you would use either Krippendorff's alpha for different types of scales, or Cronbach's alpha if your scale is kind of interval. So if you are interested in expert ratings, you can just follow this link and see how you can quantify this inter-rater reliability. So Friedman's ANOVA is a very rare thing that I've never seen being used in my life in practical analysis. So just to sum it up, if you have more than 2 independent samples, you can use either ANOVA if you have normal distribution balanced groups with equal variances, or you can use Welch's ANOVA if you have unequal variances, or you can use Kruskal-Wallis if you have a non-normal distribution or ordinal scale. And similarly for dependent samples, or we'll say for repeated measures, you use either repeated measures ANOVA or its non-parametric alternatives. Or you might want to look into some expert agreement statistics if your repeated measures are observations by different experts of the same objects. And of course, we'll come back to different types of ANOVA when we take a look at more complicated situations where we have several independent variables at once.